Yeah, Matt, thank you for the introduction. And yeah, to start off, I will go through the related work, both of ReSTIR and photon mapping, to get you all on the same page. So we start with photon mapping. So photon mapping essentially is a two-pass global elimination algorithm, where on the first pass, the photons are generated from the light source and traced through the scene. And then in a second path, we trace camera rays until the first diffuse hit. And on this first diffuse hit, the photons are collected within a radius. This radius is fixed. And photon mapping is able to produce, for example, these renderings. But as the collection happens with a fixed radius, even with sufficient samples, photon mapping can always appear a bit blurry. However, this can be fixed using stochastic progressive photon mapping, where the radius is reduced with every frame. And if I switch back between the slides, you should see that the caustics are more sharp after the same amount of iterations. With stochastic progressive photon mapping, you are able to render consistent images. However, stochastic progressive photon mapping is normally a CPU algorithm, and as we know, CPU algorithms are quite slow and not suitable for real time. But in our recent work, we introduced a GPU-optimized version of stochastic progressive photon mapping, which I will now quickly go through. This was a three-pass algorithm. So on the first pass, we trace until the first diffuse hit. And these hits are then stored in buffer. And we also mark the position of the hit in a binary word space hash grid for later use. Then on the second pass, we generate the photons. And then we use the hash grid, the binary hash grid from last frame, to essentially check if the photon will be collected at this point or not. And all photons that are outside of marked cells, they can be culled. And this is important as for an acceleration structure, which is the expensive part for photon mapping, where we will collect them, we use inverse radius search, where the radius is mapped to the photons instead of the search query. And basically, these photons are then stored as real 3D spheres in a ray tracing acceleration structure. So we use the hardware to basically collect them in the third pass, where a small ray is distributed from the hit point, which we distributed in the first pass, and then the photons can be collected in the ray tracing shader. And this is quite fast. So next up, we get to resampling, and for this I will explain ReSTIR using the example of direct light. So normally, when sampling uniformly or when evaluating light in real time, we often cannot really afford to distribute more than one visibility ray. So for sampling a scene with that many lights, this means we just pick one at random, and maybe it's a good sample, but often not, as you see, and this can result in a very noisy image. But even if we get a good sample, as we sample uniformly, it can also happen that many samples are outside of the view, or also they have a valid view, but it will not contribute much. This can be improved with resampled importance sampling, where an M amount of candidates are generated, are used in RIS to select one good sample. To select this one sample, target function is used, and this target function is somewhat proportional to the real sample distribution, but easier to calculate. For direct light, this could be the unoccluded light contribution. And this is then used to select one sample, and this one sample, for this one sample, we evaluate the visibility ray. This results in a much better image, as you can see. Together with this one sample, we also get unbiased risk weight, which is used together with the selected sample to shade the final pixel. And Bitterly and colleagues noticed that while you can resample, candidates generated at 1 pixel, why not also use the information from past iterations or neighboring frames? As we already know, these are probably good samples. So this is what ReSTIR does. They also resample the RIS samples from past pixels and also from a neighboring pixel. ReSTIR was also used already on global elimination. Here we can see a 1 sample per pixel path tracing image, and ReSTIR GI traces one path and resamples the hit at the first diffuse hit. But this does not really work well on specular materials, as these paths have a very small lobe and often cannot be resampled. Then there's also ReSTIR PT, which is a prototype in the generalized resampled importance sampling paper. And there they used shift mappings and also generalized the resampling formula. And their shift mapping, especially hybrid shift mapping, helps resampling on specular materials. And then there's also the recent prototype of suffix ReSTIR from the conditionalized resampled importance sampling paper, where they solved correlation and disocclusion artifacts that still happen in ReSTIR PT by deferring the resampling process to the second bounce, and also using a final gather step at the second bounce to resample other nearby reservoirs. However, all of these global elimination resampling algorithms fail at rendering caustics, as we can see here in the cookie jar, or it's a glass jar. ReSTIR GI completely fails to find or to resample any path. They can find these paths with a very low probability, and then they often disappear very fast, so you don't see them. ReSTIR PT is somewhat able to find these paths, use a reconnection shift to find these caustics. However, they are riddled by many correlation artifacts, and suffix ReSTIR also does not find any caustics. And the work I will introduce now, or the algorithm, is actually able to render these caustics with 1 sample per pixel. So for this, I will first introduce an optimized version of Photon final gathering. So we start by generating an array from our camera and tracing that one until the first diffuse hit point. And from this point out, we will distribute our samples from the point using importance sampling. And these finite gather samples are then used to collect these photons later on. Then we distribute the photons from the light source, and photons are either categorized as caustic photons if they were refracted or reflected by a highly specular material, such as a glass sphere, and as global photons else. Again, we use the inverse radius search, so the radius gets mapped to the photons, and they will be used to build an acceleration structure. And we can also apply our culling to reduce the number of photons in the acceleration structure beforehand. And then again, we will use an infinitely small array to collect the photons. For final gathering, we actually want to directly display the caustic photons. So at our first diffuse hit, which is the green square, we directly collect all caustic photons. And at our final gather hit, we collect all photons. And with this, we have a fast GPU-based photon final gathering algorithm, which, as you saw at the start, still is quite noisy with 1 sample per pixel and only converges when accumulating. So next up, we fix this by resampling. for this, we look at this example where I distributed basically 2 samples, and each reservoir is initialized at the first diffuse hit, which is the green square, and our ReSTIR sample is basically our final gather sample, which is used to evaluate the indirect light at this point. At this point, of course, photon collection already happened, so we start basically at the end of our final gathering. Now we move the camera and distribute a new sample, which coincidentally lies at the bottom of the old path, or at the reprojected point of the old path. We generate a new reservoir by distributing a new final gather sample and also collect the photons at the sample. And then we basically use ReSTIR or RIS to select one of these samples. Also, we need to apply reconnection shift to accommodate for the changed generation PDFs, which is actually quite easy for this case. So you just use the changed Jacobian determinants. And then, yeah, basically RIS chooses one of these 3 samples, and this sample together with the RIS weight can be used to shape the final pixel. So now we have stable global illumination in real time. But maybe you noticed the photons, the caustic photons, are still splatting all around, and this is not really good. So let's fix this by adding another resampling pass. So we now look at our first diffuse hit from a top-down perspective. For convenience, I now map the radius to the point. We distribute the photons in our scene, and now we just use RIS to select one of these photons. So basically our diffuse hit point is our reservoir, and each caustic photon is one sample. And this one sample, together with the RIS rate, basically represents the photons. Then we distribute new caustic photons in the next iteration. Also choose one photon with RIS. And now we can just combine those reservoirs as normally in RIS. And then we have our one photon with the RIS rate, which again can be used to shade our image. As you can see, caustics are much more stable now in real time. Both images offer both images the same amount of photons are distributed. And these paths can also be accumulated, so this is after 1 minute. And caustics do not show any obvious correlation effects. Now, to compare our work, or to evaluate our work, we compared it with the previous shown works of path tracing-based global illumination resampling algorithms. The times shown are captured with an NVIDIA RTX 3070 Ti. And we also use the author's implementation and to compare them with our. And as you can see, suffix ReSTIR and ReSTIR GI really fail to find any of the blue paths reflected from the glass surrounding the light source on the top left, while ReSTIR PT is still able to find those, but they are quite noisy. And while our ReSTIR final gathering is able to uniformly display this indirect light refracted by the blue glass. In terms of render times, we are around the same time as ReSTIR GI. In the scene, we are a bit slower, but there are also some other scenes where we were a bit faster and are quite faster than ReSTIR PT and suffix ReSTIR. We also tested scenes where ReSTIR GI and PT were very prone to exhibit correlation, such as the kitchen scene. And our ReSTIR final gathering very rarely displays those kinds of correlation at these scenes, as we collect the paths that are very prone to cause these correlations. We directly collect them in the form of caustics. But we are not completely free. They can happen, but they happen very rarely. It should also be mentioned that suffix ReSTIR is also free of correlations, but overall more noisy. We also tested our ReSTIR with denoising. So we used NVIDIA's real-time denoiser to show that as a proof of concept, our ReSTIR work can be denoised. And we also tested our ReSTIR with real light sources, where the emitter is surrounded by glass. And our ReSTIR fine gather is actually able to reuse these paths in the form of caustics. So we can display them where the others either completely fail or are riddled with very obvious correlation artifacts. So in conclusion, we introduced a combination of light tracing and ReSTIR. It also introduced photon collection as a ReSTIR process, and this allows for complete indirect elimination in real time with well-defined caustics. For future work, one could develop a photon denoiser, as most denoisers are specialized on high frequency noise. A photon denoiser would then work on these low frequency photon blobs, which could especially improve the quality of the caustics. Then our work could be combined with photon guiding to trace less photons on places of the scene where they would not be collected anyway, or also to improve performance on bigger scenes. And we could also combine our work with the hybrid shift until the first diffuse surface, as that could improve quality on high specular surfaces such as glass and metals. And then I thank you very much for your attention. We also have full source code, a demo, and additional resources at our GitHub link, so you can also try our resampling algorithm.